Welcome to our September 2024 meeting. Tonight's topic is Design of the Universe, Part 2. We are the Triangle Apologetics community. We're a group of men and women from diverse age groups, backgrounds, and levels of education who are interested in scientific research and evidence that point to God's existence, character, and the Bible's reliability. Our topics lean toward STEM topics, but we're not limited to those. And we partner with a variety of scholars in various fields and trained apologists sharing videos and presentations. We were formerly known as the RTB Raleigh, North Carolina chapter. Next month in October, we will be hosting a live stream of the general sessions of the Steadfast Apologetics and Evangelism National Conference, Friday evening at 6:30 p.m. and Saturday afternoon starting at 3:15 p.m. You're welcome to join us. Please let us know if you're planning to be here. We usually have some food here. There's the conference link right there. All right. Recent advances in physics and cosmology show us how incredibly profound the design of the universe is and how carefully staged it is for life in general and human life in particular. Are these just amazing coincidences, or is there something else going on here? In this presentation, as I did in part one, we'll talk about various definitions as we go along. And so here again, cosmology is the science of the origin and development of the universe. And the cosmos is an orderly, harmonious, systematic universe. Uh, Once again, we're going to ask the question, or we're going to talk about the surprise principle. This is a principle about evaluating evidence that is observed. This principle guides us to select the hypothesis that best explains the evidence and to reject the hypothesis that leaves us completely surprised in the face of the evidence. And I'll get to some examples here in just a moment. One other thing, this is not describing a person's unfamiliarity or surprise with a new idea. This is simply about how to evaluate evidence. All right, so here's the more formal definition of the surprise principle. For two hypotheses, H1 and H2, the observation O strongly favors H1 over H2 if and only if H1 were true, you would expect O to be true. That is, O would not be surprising. If H2 were true, you would expect O to be false. In other words, O would be very surprising. Now, this does not necessarily mean that H1 is true based on this principle alone. You have to use other things to help you come to that conclusion. However, it means that it's much more likely to be true than H2. So we're working at getting to the inference to the best explanation. So I've got two examples here, and let's talk about the first one here. First of all, we need a little background on this first example. This is a royal flush hand in poker. So if you're familiar with poker, you've probably heard of this. In this particular version of poker that I'm talking about, this is a 5-card poker, no-hole cards, regular 52-card deck, freshly shuffled. This is the standard sort of poker. This is unlike a 7-card poker where the odds are actually easier for you. So we're taking the most difficult case here. A royal flush, of course, is a very high or the highest ranking hand in poker. The odds of getting a royal flush in a game with these parameters, including the freshly shuffled deck, are 649,739 to 1. This is a widely known number. You can look this up anywhere you want to look, basically. If you convert this to a probability, in other words, what's the chance of it happening one time? The probability is approximately 1.5 times 10 to the minus 6. That's where we are with how likely this is to occur. All right, so given that background, here's our where we invoke the surprise principle to talk about an observation that we make. So here's an observation. A player received 10 royal flushes in a row, and the probability of that happening is simply taking the probability of one of them happening, and because these are independent events, assuming the deck's freshly shoveled and all and so forth, then you would simply multiply those times 10 because there's 10 in a row here. So the probability of this occurring, of a player receiving 10 royal flushes in a row, is approximately 7.4 times 10 to the minus 60. So given this observation, we have two hypotheses we're considering. One hypothesis, H1, is that the deck was stacked. The other hypothesis, H2, is that this occurred by pure chance. So, for any of you who play poker, how often has this occurred to you where you receive 10 royal flushes in a row? I suspect probably never, although I could be surprised, I'm sure. Um, so, if a new player comes in, let's just say, and you're playing a game of poker, and a new player comes in, and this new player receives 10 royal flushes in a row, just 10 hands in a row. Um, are you surprised at this? If the deck was stacked, if you knew the deck was stacked, would that be a surprising outcome? You might not like the outcome if it was stacked, in this case, if the player was playing against you. Or are you more likely to think, no, this was pure chance. This is just pure chance. I think most people would agree that you would say, no, the deck was stacked in this case to receive 10 royal flushes in a row. As I mentioned when I talked about this in part one of the design a while back, I did look this up and I looked around for any poker tournaments where it was the news was that somebody got more than one royal flush in a tournament. I did find one. There was a weekend tournament at a retirement center, and this guy was playing poker and he received two royal flushes during the course of the whole weekend, but certainly not back to back, in two hands back to back. So this is the surprise principle. If you say the deck was stacked, then yeah, of course you would think this was certainly a possible and even plausible observation. If the but to say this was by pure chance is probably that's a very tiny number. That's 7.4 times 10 to the minus 60. Now I will ask you to remember that number because we're going to come back to that later on. Now let's talk about a second example. Doesn't require any background explanation. Here's the observation. The message, "Happy birthday, Dennis Martin," was observed written with seashells while walking along the beach. Uh, H1, this is of course referring to me because my name is Dennis Martin. The first hypothesis, I was visiting some friends at their beach property on my birthday. And H2, another hypothesis would be, there was a storm 2 days prior and the message was caused by the natural forces of the wind, surf, and tides. So given the observation, given we know about how things like this work, it seems to me that H1 is much more likely to be true than H2. And in fact, this is where I can invoke a little bit of computer science because that's my background. The message, "Happy birthday, Dennis Martin," actually fits the description of information. And we know that information only comes from minds. It does not come from physical forces. So that's another um, point in the favor of H1 being the correct hypothesis here that most likely explains this message. All right, so now we've got those two out of the way. Let's keep those in mind as we go along, but let's now get into the meat of the presentation here. This presentation is part two of going through the book Designed to the Core by Hugh Ross. In this presentation, except as noted, most of the following material, I'm either quoting it directly or paraphrasing it just to kind of summarize it from the book. This is a 374-page book. It's filled with hundreds of citations from scientific journals, articles, and so forth, and I'll be quoting a bunch of those. The book itself is very dense, and I was originally going to do all of this in one presentation, but it's just way too much to do in one presentation. So we're going to go through, this is what I'm calling part two, but let me give a little bit more introduction to this book for those who haven't heard about it. This is a quote from Michael Strauss, who's a David Ross Boyd Professor of Physics at the University of Oklahoma, who is also presented to this group. He says this, "In Design to the Core, Dr. Hugh Ross takes us on an unprecedented journey to explore the necessary requirements for a planet to support complex life. His truly comprehensive approach to the subject examines every aspect of Earth's life-friendly environment, from the cosmic supercluster that we inhabit, to our location in the Milky Way, to our unusual solar system, and even deep inside the Earth's core. The sheer number and scope of the needed parameters is mind-boggling and unambiguously answers the question of whether Earth is unique in its capability of supporting complex life. The only question left for the reader to ponder is how such a fortunate planet could have come into existence at all. Many of us who have pondered that question will agree with Dr. Ross that such exquisite design requires an intelligent and powerful designer." All right, so I'm going to give just a quick overview of a little bit from part one, just to kind of uh, get us kind of reset back into this mode of this design to the core content. So we're going to do just briefly a couple of things that we talked about in part one, and then we'll jump right into part two. So the first point, just as a just to remember here, is this concept of fine tuning. Uh, in 1989, scientists noted that there were 15 features that were finely tuned about our galaxy and our universe and that sort of thing, features of the cosmos as a whole. But over the years, the number has gotten higher and higher. And so at last count in 2006 anyway, there were 140 features that required fine tuning for the possibility of life to exist here. So you see the trend here seems to be going up. More and more things we're discovering as scientists look into lots of different things. There's more and more things that, oh yeah, that has to be fine-tuned. Oh yeah, this has to be fine-tuned. So that's just one of the items we talked about last time. Another one about nearby galaxy superclusters. No superclusters of galaxies are located near enough to our nearby superclusters and Laniakea, which is the one we're in particular, to pose a threat to life or the possibility of life here. However, if the entire observable universe were as devoid of galaxy superclusters as our immediate region, the universe would not be conducive to life at all. We have the right mix of uniformity versus non-uniformity and homogeneous versus non-homogeneous. Basically, what this means is that we're in a special pocket, and not only at the super galaxy cluster, which is the largest kind of structures there are in the universe, and then further on down as we look at other ones, there's just like a specialness about the pocket we're in, which is more conducive to life than the rest of the rest of the universe as we know it. So again, and you'll see this throughout the book, we have the right mix of uniformity and non-uniformity, homogeneous versus non-homogeneous structures, and we'll get into some of those. One other thing we talked about last time was the Milky Way galaxy. So let me just review a few things from that. The Milky Way galaxy is unique in multiple respects, all of which have bearing on its capacity to host an advanced life site. The long list of extraordinary features includes these. I won't read all of these. I'll just pick out a couple of these here. Um, Number four, an astonishingly small, extremely quiescent supermassive black hole. We'll talk more about that in a little while. The number of spiral arms and their precise pitch angle, uh, the green hue from the proper balance of old, middle age, and young stars. All of these things, and we talked about these last time, all of these things go to make it unique and especially conducive for life, not just basic life, but advanced life, like human beings. All right, with all of that, let's now jump into part two. In part two of this series, we're doing these items here. We're going to talk about our solar system, our sun, something known as planetary migration and orbital configuration. We're going to talk about exoplanets, and we're going to talk about our moon. The book further goes into the Earth itself and the crust and the mantle and all kinds of other things, but there's just so much content that I couldn't even get to that. So this is what we're going to cover in part two. First of all, let's look at our position in the Milky Way galaxy. We've got two diagrams here. The one on the left is from the National Radio Astronomical Observatory. The one on the right is from the Webb telescope, and you can see the link for that image there. Basically, this is a diagram of the Milky Way galaxy, and you see the spiral arms. A couple of these are named, the Sagittarius arm and the Perseus arm. And then you see our sun, which is in this local arm, but it's kind of not close to any of the bigger arms. So that's one particular thing you'll notice about this here. Uh, and you also see the picture on the right, of course, talks about it from the side view. There's this disk with the central bulge in the middle, and we're kind of out away from that. This is like being not in downtown a big city as far as light and radiation and all that, but we're out, kind of in the suburbs here where you can actually, it's not quite so noisy from a radiation standpoint. So you can see in both of these, they have the location of our solar system and our sun. So we're not in the dense part of the galaxy here, or yeah, the Milky Way galaxy. As far as we can tell, there's only one small region within the Milky Way galaxy that has the features that advanced life requires. And we're going to talk about a bunch of these. Um, One of them, let's talk about a couple right here. The areas nearest to our sun in the Sagittarius arm and the Perseus arm contain only small to medium-sized star-forming nebulae and, and star clusters and no large ones. We're protected from any major gravitational disturbances or life-threatening radiation from these two arms. These do not just does a planet have gravity and a star have gravity, but star clusters like this and regions of stars that produce them, the whole region also has gravity that affects other things. So as these arms move, and we'll talk about that in a little bit, you have to be concerned about not only just the gravity from an individual planet or star, but groups of stars as well. And so we're protected from any major gravitational disturbances or life-threatening radiation from these two arms. The Orion Nebula in our local arm is sufficiently distant, and the nearest star clusters are also sufficiently distant to pose no threat to us as far as life on our planet and our solar system, but specifically on our planet. All right, let's talk about black holes. There are three basic types of black holes. There's the stellar mass black hole, which is a black hole that's about the same size as a typical star. Uh, there's the supermassive black hole, which we'll talk about in a second, and then there's this intermediate mass black hole. The Milky Way galaxy supermassive black hole at the center, which is where you find these supermassive black holes typically, is approximately 4 million times more massive than our sun, but is relatively small compared to other galaxies. And that's an interesting point. Also, there are dozens of known stellar mass black holes in the Milky Way galaxy, but they're sufficiently small and distant to pose no threat to us. When we talk about supermassive black holes, just about every galaxy has a big one right in the center of it because that's kind of holding the whole thing together. But of course, it has lots of radiation and all that. And obviously, you don't want to get too close to a supermassive black hole. All right, another item in our galaxy is our pulsars. These are highly magnetized neutron stars that emit narrow beams of intense electromagnetic radiation. And they resemble lighthouses in that they rotate and their beam of rotation rotates with them. And these rotation rates are measured in, it can be very quick, down to milliseconds and up to seconds. So it's a very strong and very fast pulsing sort of star. There are only 11 pulsars within 1,000 light years of the sun, and the nearest one is more than 500 light years. So these are sufficiently far away that they pose no threat. If you're close to one of these, you get these electromagnetic, beams, and it can be very dangerous to life. All right, here's another thing. The co-rotation distance. This is something really interesting, and you see this with spiral galaxies. This is the distance from the galactic center where stars revolve at the same rate as the spiral structure itself rotates. So remember, the whole structure is rotating, and the stars in the galaxy are rotating around the center point or the center hub, if you want to call it that, of the galaxy. So stars that are inside this co-rotation distance rotate faster than the whole structure itself. Stars that are outside of the co-rotation distance rotate slower. So stars not near the co-rotation radius uh, are crossed by or can be crossed by spiral arms that contain other stars, clouds, and nebulae that gravitationally can disturb them, resulting in increased bombardment of radiation or comets or whatever on the planet. So if you're not near the co-rotation distance, the structure is moving at one rate, and the stars, and of course the planets that are going around those stars, move either faster or slower, and so there are going to be some collisions and disturbances, if nothing else, if not collisions, at least gravitational disturbances. Stars at the exact co-rotation distance, right on that circle there that you see in the picture, uh, if they're exactly in that location, then they experience this, what we call destructive mean motion resonances. That's because frequencies are doubling up. So the best way I can think about this, or I can describe it, is thinking about music, for example, and thinking about a piano. If you play a note, let's say middle C on the piano, there's a certain sound that it makes. And then if you go up an octave and play the next C up, and you play them together, not only do you get the two sounds, but you also get this sort of harmonic and this resonance because both of them are at this are the same they're the same note. It's just that one's at a higher frequency, but it's double the frequency. So there's this resonance that happens when you have these things exactly like this. So that's the closest thing I can think of to describing this problem. Now, as it turns out, our sun is at 98% of the co-rotation radius, which is really the safest place to be to sustain advanced life for any length of time, because we're almost going the same speed as the structure itself, and we're in a location that's conveniently sparse as we move around, and at least for the time period, and we'll talk about some time periods here in a minute. Um, we're in a very safe position. So as you start to think about all these things that are lining up, it's like, that's interesting. Why are we in exactly that spot? But anyway, that's where we are. 98% of the co-rotation distance, that is the safest place to be. All right, another interesting factor is something called the local bubble. Our sun resides in the middle of what's known as a rare and temporary feature called the local bubble. It's a magnetized cavity or void of exceptionally low density gas extending 160 to 640 light years in all directions from the sun. And you can see a diagram of it there. This is from an astronomical journal. You see our sun is right there. And so that just means there's less stuff right close by that could interfere with life. It's just amazingly interesting that we're in this local bubble here. All right, let's talk about the G dwarf problem. And we're going to talk about star types here, but our star is a G dwarf star. G dwarf stars burn hydrogen with a mass measuring 0.7 to 1.0 of the mass of our sun. So that means slightly smaller than our sun, all the way up to about the same size as our sun. Generally, the older the star, the lower the metallicity in that star. And you need sufficient metals, some of the heavier elements or slightly heavier elements, these are required to sustain advanced life. Some stars in the sun's vicinity are metal rich, including our sun, while others are metal poor. Based on its distance from the center and its age, our sun has more metals than would be normally expected in this case. Scientists have deduced that our sun migrated from a metal-rich area of the galaxy, which is closer to the middle, to its current safest for life location as it is now. And you can see the picture there. So our sun apparently has migrated from the metal-rich area, which is also more radiation and so forth, to this very safe area. Safe is at least in terms of life. So another interesting thing that's happened. So our sun didn't always used to be where it is right now, relative to the rest of the galaxy. All right, no recent supernovae. All right. In spiral galaxies most similar to the Milky Way galaxy, astronomers observe the occurrence of supernovae at the rate of about 3 per century. These explosions at the end of a massive star's burning cycle can, temporarily at least, outshine an entire galaxy. These are just massive. And of course, there's lots of radiation and light coming off of that. For our sun in its current location, supernovae within 5,000 light years occur on average about once every 300 years. Closer to 1,000 light years, about once every 10,000 years. Now, have been some recording of these events. In 81,006, there was an event 5,080 light years away. In 1054, there was an event 6,500 light years away, a supernova, and that one produced the Crab Nebula. However, supernovae beyond 5,000 light years have no measurable impact on advanced life or crop production. However, they are spectacular events. Uh, Once again, our sun is in a remarkably ideal location, especially for sustaining advanced life, because relatively few supernovae, and the ones that are far enough away that it's not a problem for us. All right, let's talk about stars. All right, we have lots of stars in the Milky Way galaxy. Stars in the universe vary in brightness, size, color, and behavior. These things, known as main sequence stars, convert hydrogen to helium in their cores by nuclear fusion, which releases visible light and other forms of radiation, including ultraviolet and X-ray light. Stars spend most of their time as main sequence stars. Solar planetary systems can have more than one star in them, and our star is classified as a type G yellow dwarf and is a main sequence star. Now, on this page, I found this chart on, it's called Atlas of the Universe. It was produced in 2006 by Richard Powell. It's a little bit dated, but still the content is basically good here. So looking at these stars, uh, across the top there, you see the spectral type is the first, and where there's a single letter. So you have O, B, A, F, G, K, and M going across. These give the temperature in Kelvin. These give the radius relative to our sun, the mass relative to our sun, the luminosity, and so forth. You can see all those statistics there. And also you can see their abundance. So on the far left, the class O stars are relatively rare, whereas on the far right, the class M stars are relatively common. In addition, you've got these other types, or they can go through different phases. So there are giant stars. Uh, they can be uh, low mass, but near the end of their lives. And you can see the categories there and some other specs there. White dwarfs are the dying remnants of an imploded star. They have their own spectral type. And then supergiant stars can be any of the, or many of the types there. And you can see some stats there. Uh, I think the interesting thing to point out, though, is in the right side, in the box there, according to NASA, the Milky Way galaxy has about 6% of its stars are type G, well, which is our sun's type. 13% are type K, and 73, by far the largest percentage, are type M. This is according to NASA. You see those percentages are slightly different than what Richard Powell had in 2006. The NASA number is probably a little better, but of course, NASA is only talking about the Milky Way galaxy. I'm not clear if the Richard Powell chart is talking about just the Milky Way or just everywhere in the universe. But anyway, let's focus on the Milky Way galaxy. So type M, of course, is the most common. And you can get more details about that at that link on NASA's website. All right, let's talk about our sun for a minute. Uh, some astronomers are looking for what they call the holy grail of another planet just like Earth. However, many of them have come to the conclusion that such a planet would have to have a host star virtually identical to our sun. So a lot of astronomers are now looking for a solar twin. And one of the reasons for that is it's a lot easier to detect stars than exoplanets. And we'll talk about the exoplanets here in a few minutes. Stars, of course, give off light, so they're easy to see with a telescope, whereas exoplanets only reflect light and they're much harder to see. So people are looking for solar twins, but rather than finding a solar twin, what people are really finding is that there's an increased awareness of our sun's unique features that specifically meet the needs of advanced life on a planet such as Earth. There's a lot more uniqueness here, so finding the solar twin actually is becoming a little more difficult than people thought. So let's talk about some of the unique things about our sun. The first one here is our sun's unique quiescence, and by that we mean stability. And let me get into this quote here. Hugh Ross says this in the book. It's been said that stars are like human beings, unstable when young and again when old, and maximally stable in middle age. Such is the case with stellar flaring activity. So these are the solar flares we'd like to talk about, or that you hear about from time to time. Solar mass stars exhibit their minimal flaring during a narrow time window in their nuclear burning history. And so you can see on the chart on the right there, this is also, Hugh Ross did this in the book. This comes from the book. You can see the lowest point of the solar flaring is right where we are right now. And I will add that just a little note from the picture, the y-axis on the left side of that chart is logarithmic, which means if you're measuring it in direct numbers, it would be much, much steeper. But logarithmic makes it a little easier to graph. So we're right in the sweet spot right now of the minimal flaring, maximum stability of our sun. All right, so that's one feature of our sun. Here's another one, the brightness of our sun. So there are some different layers in the sun. So the photosphere is the visible surface of the sun and it's the light that we see. Obviously, there's not land on the sun like there is on the planet, so it's a different kind of surface. But anyway, it's about 5,500 degrees C or Celsius, 9,900 degrees Fahrenheit. And then right above the photosphere is something called the chromosphere. This is an irregular layer just above there that has where the color, and mostly reddish due to hydrogen, and is much hotter than the photosphere. But as it turns out, our sun is photospherically and chromospherically stable, unlike most other stars of its type. And so the chart on the right shows a study of 369 stars where they measured the brightness variations in the sun and all these other stars. And the top chart is the brightness variation from our sun, and the bottom chart is the brightness variation of all the rest of the stars, just averaged together. And you can see the other stars, it's much more variability in brightness than in our sun. So again, you're looking for stability, and if you're going to support life, you need things to be stay within a certain stable range. All right, so he says, Hugh Ross says this in the book. This alignment of specific solar time window seems uncanny. The sun exhibits a period of maximal luminosity stability and minimal flaring activity in terms of rate and intensity, and is free of superflares. These events occur just as the sun reaches the safest position in terms of potential gravitational disturbances and radiation exposure in its quarter-billion-year orbit around the Milky Way galaxy center. All of these coincide with an era of exceptional quiescence for the Milky Way galaxy's supermassive black hole and an era free of nearby supernovae and gamma ray bursts. Such alignment defies all reasonable probability estimates. Somehow, multiple independent time windows involving both the sun's neighborhood and favorable for life internal features perfectly aligned. So that's really interesting. There's a whole bunch of things that are just right now for life to exist on Earth that we just don't see in other systems. So it's just really interesting. All right, let's take a look at our solar system. This chart, by the way, which is not to scale, is in a, you can see the link down there from the StarNet libraries. So in our solar system, we have one star, we have 8 planets, fully qualified planets, that is. We have 5 named dwarf planets, hundreds of moons, thousands of comets, and more than 1 million asteroids. And you can see there are 2 asteroid belts there. There's the asteroid belt between Mars and Jupiter, and then there's the Kuiper belt out past Pluto. Uh, our solar system orbits the center of the Milky Way galaxy at about 515,000 miles per hour, or about 828,000 kilometers per hour. It takes about 230 million years to complete one orbit, and that's this whole system orbiting around the center of the Milky Way galaxy. And some of this data is from NASA, as you can see there. All right, so that's just an idea. Now, keep in mind, this is not to scale. If this were to scale, the planets would be much further away than they look in this diagram. All right, so typically when we talk about planets, whether they be in our solar system or exoplanets in other solar systems, we talk about distances from the sun. And so uh, astronomers have come up with this thing called the astronomical unit. And 1 astronomical unit is approximately the distance, the average distance between the Earth and the sun. You know, just as a side note, the Earth does not have a perfectly circular orbit around the sun. It's a little bit elliptical. So it's sometimes a little more than this, sometimes less, but this is the average distance. And so we call it 1 astronomical unit. And so NASA put together this video you can watch if you want to get more details about this. And they compare the distances of our planets in our solar system to a football field, an American football field of 100 yards. So as you see, you can see the football field down at the bottom there. And the yellow lines represent where some of these planets are. The Earth is at about the 2 yard line on this football field sort of scale. Mercury and Venus, of course, are much less than 1 yard. Mars is about 1.5 yards out. And then the other planets you can see there, Jupiter, Saturn, and so on. You can see where they are. Uh, Jupiter and Saturn are before the 50-yard line. The other 3 are after the 50-yard, or Neptune's at the 40. And then anyway, you get the idea. So you can see just for scale, this is how far away these would be. And you can see that you can go to NASA's website and get the details of where where the planets line up on these astronomical unit scales. All right, so there is a search for another planet like Earth. I mean, that's really interesting. And so uh, it's not just that people want to see what other planets are in other solar systems, but specifically, there's a lot of interest in a search for another planet like Earth that can possibly host and sustain life. And so, what people have come to the conclusion about is that there's a growing recognition that such a planet would need to be part of a planetary system with a population, that is, a population of planets, and configuration similar to our solar system. As a result, they're not just looking for an Earth twin, but now they're looking for a solar system twin. At a minimum, this means a star and a set of planets, and particularly a set of planets in a particular arrangement. You can't just have any star with any kind of planets for it to have life anyway. So the word exoplanet is the word that means a planet that orbits a star outside of our solar system. So any other solar system that has planets, we call those exoplanets. All right, so as of September 12th, just before this meeting here, uh, NASA has this chart and they update this on a regular basis on exoplanets discovered. So this is what they have discovered as of September 12th of 2024. And I added the little box inside the diagram on the right, which just shows the percentages of the total, just to help you figure that out. So you can see they've listed 5,756 planets, and you can see the breakdown into Neptune-like gas giant, super Earth, terrestrial, and unknown, which we'll explain on the next chart. Uh, on the right here, you see some history. So in January of 2011, they had discovered 500 exoplanets, and then you can see the progress over the last few years, especially the last 2 or 3 years here. 4,000 in 2019, 5,000 in 2022, and 5,500 in July of 2024. And now in September, we're up to 5,756. And presumably they'll keep updating this as they go along. Anyway, so keep in mind, well, let's go on here and I'll come back to some numbers here in a minute. All right, so this is another chart that NASA provides on the different types of exoplanets. So on the far left, you see the big yellow one there. Those are the gas giants, the size of Saturn or Jupiter, or sometimes much larger. They also include something called hot Jupiters. They talk about where they are, and I'll get to something called the ice line in a minute. If they're in close to the sun, then they're called hot. If they're out far away, they're called cold or cool. Neptune-like planets. We have terrestrial planets. We have super Earth planets. So super Earth planets are basically like terrestrial, but they're much bigger than Earth, but they're lighter than Neptune. Whereas the terrestrial planets are the Earth size or smaller, mostly made of rock and metal. Some could possess oceans or atmospheres and perhaps other signs of habitability. Terrestrial planets are the prime candidates to support life. The other ones, really, there's too much wrong with them as far as life is concerned. You can't have life on those other ones. The only one that really can host life, certainly as we know it, are the terrestrial planets. Um, Most terrestrial exoplanets discovered so far orbit their host star at a distance less than Mercury's distance from the sun. So that's just kind of interesting. They're so close, so there are obviously going to be some problems for terrestrial planets orbiting their star that close to their host star. All right, so there's some data here in the book. The book was published in 2022. The data was collected in September of 2021. So that's the data here that he's using here, and I'm going to show a comparison in just a little bit. So looking at exoplanetary systems, what we see primarily is the difference between our solar system and other solar systems with planets. The exoplanetary systems, they have hot Rockies, which are the rocky planets that are or terrestrials that are very close to the sun. And you can see the astronomical unit measurements there at the bottom. And there are warm Rockies, but we don't see uh, other solar systems that have cool Rockies, whereas the Earth, uh, is a cool Rocky. All right, so that's on the left side. On the right side, this is the relative populations of the known exoplanets, again, as of September of 2021. And you can see the percentages there. The rocky planets, 3.7%, and you can see the other ones there all in the 30+% range, making up the full 100%. Since the book was published, an additional 1,200 exoplanets have been discovered. And so what I've decided to do here is just overlay this chart with the percentages that you saw on the other chart. And so you see those in green there on the right-hand chart. as of September 12th, the percentages are this. So they're very similar. Um, the relative distribution of the uh, exoplanet types hasn't really changed that much from uh, from 2021. So here we are in late 2024. Uh, Percentages are about the same, but basically the rocky planets are really the only ones that are good candidates for life, and that percentage hasn't changed much either. It's still very small at 3.6%. All right, let's look at some of the other kinds of planets that are in these other systems compared to our solar system. All right, so we have warm Neptunes and warm super Earths, which of course we don't have any of in our system. We have cool Neptunes. We have cold Neptunes in some, a very small percentage of cold Neptunes in some of the other systems, the other exoplanetary systems, whereas we have a higher percentage of cold Neptunes in ours. And we have some small percentage of rocky in the other ones, but we have a lot more Rockies in ours. And so you get the picture there. They're just different by a lot. If you look on the right-hand chart, uh, these are the giant population, the giant planets here. See the percentage of warm giants, cold giants, cool giants, and distant giants. All right. We have only cold giants in our solar system, whereas you see all kinds of other stuff. Um, there's actually an anti-correlation here. Warm gas giants, planets more massive than Saturn, orbiting their host stars more closely than 1 astronomical unit, that means more closely than our Earth is to our sun, frequently occur in these planetary systems. When these are present, however, rocky planets, warm or cool, are missing. So you get a lot of, so if you see a lot of these big giants, that means there's probably not going to be any kind of rocky planet, which means, again, no life. All right, so let's talk about the benefits of cold gas giants. Hugh says this in the book. He says two things here. The first one is for life to be possible in a planetary system, any habitable rocky planet would require cold gas giant companions. These cold gas giants would be needed to gravitationally shield the habitable planet from too many asteroid and comet impacts. For shielding to be adequately protective without disturbing the rocky planet's orbit, it must come from more than one cold gas giant. More specifically, the cold gas giant planets must be arrayed on a widely spaced orbits. If not, the habitable planet's rotation axis would tilt. That tilt would vary by such a significant degree as to induce extreme climate fluctuations and climate instabilities. However, wide orbital separations for pairs of cold and cool gas giant planets are rare. So you got to have these gas giants out there, and we've seen, it's made the news where a comet or some kind of asteroid, crashes into Jupiter. We've heard about that, and that's exactly Jupiter's doing exactly what it's supposed to do. It's supposed to absorb those things so they don't hit Earth. All right, but we're finding our configuration of cold gas giants. We have Jupiter and Saturn, and they are far enough apart and in different orbital things so they don't mess up the Earth's axial tilt, which we'll get to in a minute. Okay, let's talk about this one, planetary habitable zones. A truly habitable planet must simultaneously reside in 11 known habitable zones, not just the liquid water habitable zone. So there's a lot you hear a lot of news about, they found the planet that's in the liquid habitable zone of the sun or the star it's around. And that's interesting. That's really interesting. But as of September 24, of the 5,600 planets discovered by astronomers, only one resides in all 11 of these known habitable zones. And so let me just list them here. I'll say them out loud, and you can look these up. And all of these mean something important to life. We're going to talk about one of them here on the next slide. So you have the liquid water zone, which everybody knows about. You also have to have ultraviolet habitable zone. You have the photosynthetic habitable zone, the tropospheric ozone habitable zone, the planetary rotation rate habitable zone, the planetary rotation axis tilt, the tidal habitable zone, the astrosphere habitable zone, the atmospheric electric field habitable zone, the Milankovitch cycles habitable zone, and the stellar magnetic wind. So you have to have all of these. All of these have their own habitable zone, and you have to have a planet that's in all of them at the same time. So far, everything we've seen, only Earth fits all of these. I'll just talk briefly about one of them, the Milankovitch cycles. That's a well-known thing. It has to do with how long the year is and the seasons and that sort of thing. There's lots of other ones here that are really interesting. Let's talk specifically, though, about the ultraviolet habitable zone. To remain in the ultraviolet safety zone, a planet must orbit its star no more than 4% nearer to or farther from Earth's orbitable distance, and the star it orbits would require sun-like stability in luminosity and flaring stability. Of the planets with an Earth-like diameter measured within 30% of Earth, which is a fairly generous saying it's like Earth, or mass, again measured within 30% of Earth, not one orbits in the appropriate distance range within the ultraviolet habitable zone. So even if some of these planets, and you've heard of probably two or three if you've looked into this, that are possibly in a liquid water habitable zone, none of those are also at the same time in the ultraviolet habitable zone, which means life can't happen there. Okay, let's talk about M dwarf planets. This is one of the ones, because there's a lot of these that are in the Milky Way galaxy, and you hear news about some of these sometimes. Let's talk about these. Astronomers have identified major challenges to the habitability of planets orbiting M dwarf stars, which are, of course, the most abundant in the Milky Way galaxy. The liquid water and ultraviolet habitability zones do not overlap. So if you've got liquid water over here and ultraviolet over here and they don't overlap, you can't have life on that kind of a planet. There is an electrically charged atmosphere combined with ultraviolet radiation, and that will dry the planet's atmosphere and surface. Typically, that's what happens in M dwarf planets or M dwarf systems. When they're very close to their star, we have this thing called tidal locking. So that's inevitable for planets in very close orbit to their star. What that means is even if the planet is rotating as it goes around the star, if it's very close to the star, eventually the tidal forces will cause it to lock so that one side always faces the star, getting, of course, very hot and lots of radiation, and the other side is always facing away from the star, which means it's very cold, and so it's very difficult to have life on such a planet because there's no good life zone there. All right, so that's when you have tidal locking, you have that problem. The other thing with M dwarf stars is they have harmful UV and X-ray radiation that's hostile to life, especially for planets in very close orbit, which is where many of the rocky planets in these kind of systems, if there are Rockies, they tend to be very close. So not candidates for life. And there's several sources here. I've listed them bottom of the slide there. Reasons to believe has one, and NASA, of course, has a couple there as well. So let me just quote from the book here again. Again, it was published in 2022 and the data was collected in 2021. So I'm going to make an update to what he said here. But here's the quote from the book. Astronomers have discovered and made measurements of more than 3,500 planetary systems. What they have seen indicates that our solar system differs substantially from what's now recognized as the norm for planetary systems, both in its population and orbital features. Just as the Sun has no twin, neither do any of the planets held in its orbit. The solar system is also the only multi-planet system yet discovered with a population and configuration that would allow for the possible existence of advanced life and, what's more, provide for the ongoing development and sustenance of a large, technologically and culturally sophisticated civilization within it. Now, of course, he wrote that in 2021 when the data was collected. As of September 12th, 2024, the confirmed total is now 5,756, so quite a bit more than the 3,500, but the conclusion is still the same. Still, no other system, no other star, no other planet has been found that fits the same criteria here. I'll make a little, just one other note on his last part of that quote there. Not only does Earth have the possibility of having life, not just simple-celled, one-celled animals, not just the the vast variety of plants and animals and human beings that we have on this planet, but also for those beings like humans who can then take advantage of the resources and build a technologically and culturally sophisticated civilization. Not just enough that you have some animals existing, but you have to have the kind of civilization that we have. In order to get to that, you need even more stuff. And what he's saying is, the other ones aren't even close. All right, let's talk about another interesting concept called planetary migration. Most planets migrate a large distance from their place of origin. This is especially true of gas giants and Neptune-type planets, which only form beyond their host star's ice line, or sometimes called snow line or frost line. This is the distance, and you see the picture of the ice line here in our current solar system. This is the distance where volatiles, that is volatile chemicals such as water, carbon dioxide, carbon monoxide, and ammonia freeze into ice grains. So beyond that ice line, those chemicals only are frozen in terms of grains or sheets of ice maybe, but it's frozen. Whereas inside the ice line, those things can then have a chance to be liquids or in some cases gases. All right, so this is the position of the solar system's ice line. So on the far left of that picture is our sun. You see Earth, you see Mars, and then there's a big gap. There's the ice line, then you see Jupiter. So in our solar system, this line is in the 3 to 4 astronomical unit range, but it's hard to pinpoint exactly because it's just a lot of variables going on here. But that's roughly where it is. Um, the ice line is 3.1 times more distance from the sun than Earth, and at least twice the distance on average than Mars. So it's out there between Mars and Jupiter. Uh, most, I'll just go into this. Most exoplanets that are gas giants or Neptune type have migrated across the ice line and orbit their host star well within the ice line. In some situations, there is little to no movement relative to the ice line and their origin location. In some rare situations, cause these planets to move further away from the ice line than their original location. There was a special on one of the, I think it was PBS or one of the other channels that show scientific documentaries. They talked about how Jupiter started out at one place, moved closer, and then moved kind of back out. Um, One of the reasons for that is it clears out a lot of debris because of the big gravity. And then later on, if a planet forms in that space where Jupiter used to be, well, that's convenient for that planet. Well, let's just take a look at this here. Um, this is what scientists have determined the location of these 4 planets, Jupiter, Saturn, Uranus, and Neptune. Jupiter and Saturn in particular migrated in a very unique pattern. And these movements help explain the mass of the inner rocky planets, the sun's unique elemental abundance ratios, and the size of the atmospheres of Venus and Earth. So you can see in the early history, both Saturn and Jupiter came a lot closer to the sun, and then they moved back out. Saturn has moved further, relatively speaking, but you can see Jupiter came in closer and then moved back out. Saturn came in really close, or drastically closer, and then has moved back out. Whereas Uranus has been out there for a while, and Neptune took a dramatic move out as well around the same time, give or take, as Saturn. Kind of interesting that both of those things happened about the same time. Um, I'll just make a third Neptune-like planet, about 10 times Earth's mass, gets ejected by a close encounter with Jupiter and or Saturn. So you can see the idea there. There's another one that got ejected and we don't know where it is now. It's not here. Anyway, so you see this migration does happen, and in some cases there's a reason for this migration. All right, let's talk about our solar system as a whole then. Research reveals that the migration history, mass, and orbital features of every planet in our solar system and of the Earth-Moon system contribute to the possible existence of advanced life on one planet, Earth. For advanced life to thrive on Earth, the orbital architecture of the solar system's 8 planets and Earth's moon must be exactly as it is. Furthermore, rather than confirming the expectations and predictions made by astronomers in the 1990s, the findings indicate that the more we learn about the solar system in comparison and contrast with exoplanetary systems, the more evidence we uncover for the utterly unique architecture of the entire system. So there's a lot of special things happening in our solar system. All right, now let's look at our moon. Our moon, the one going around the Earth, is the most massive relative to the planet it orbits by 50 times or more compared to the other planets in our solar system. We all know that Jupiter and Saturn have lots of moons, but they're all relatively tiny compared to those two planets. But in our case, that's not the case here. However, if our moon were just 2% more massive, greater axial tilt variability would be introduced. And I'll talk more about that in a second. If it was 2% less massive, the tidal forces would not slow Earth's rotation to be 24 hours. Because of our moon being the mass that it stabilizes the Earth rotation to 24 hours, which, as it turns out, is optimal for advanced life. Faster rotation than 24 hours would generate greater temperature and climate extremes that would limit the growth of human populations. Slower rotation will result in greater day to night temperature extremes and would affect health and crop growth. So our moon stabilizes the Earth rotation axis tilt to only a 1.2% difference over a 41,040-year cycle. By contrast, Mars's axial tilt can vary by 60 degrees. So imagine summer and winter and the seasons on a planet like that compared to our Earth, where the seasons are relatively stable. All right, let's talk about the moon's brightness. If the moon's diameter were larger or it orbited closer to the Earth, it would be so bright that terrestrial mammals would have difficulty sleeping at night. If the moon's diameter were smaller or it orbited a little further away, terrestrial herbivores would face greater difficulty foraging at night. As a result, they would be easier prey or would suffer spending excessive energy avoiding predators. So our moon's brightness is at a certain level, and that works out in favor of some things as you see here. All right, now let's talk about our moon's role as an eclipser. Many of the scientific insights regarding the sun and its behavior have come through observational data from multiple perfect solar eclipses. Solar eclipses have allowed historians to produce a calendar of events from humanity's early history. Solar eclipses have also helped confirm that gravity can bend light. We live on the only planet in the solar system that has perfect solar eclipses. Interestingly, also, this planet is also the only one with observers of solar eclipses. If you're on any other planet that has moons, the moons are so tiny relative to the planet, you can't have a solar eclipse. It just doesn't work. All right, let's talk about moon's magnetic field. The moon currently has a weak magnetic field, about 1,000 times weaker than Earth's. In the formative times for the Earth and the moon had a much stronger magnetic field and was able to help shield the Earth from the young sun's more intense radiation. Remember we talked about stars in their youth have more radiation. You remember the solar flaring chart on the far left of that graph. Remember it was much higher. So in this time, the moon was more in front of the Earth relative to the sun, and that magnetic field, because it was stronger, actually had an effect to protect the Earth. Whereas now it's much weaker, and as it rotates around, doesn't help that much. But we don't need it as much now because our sun isn't as uh, radiant, if you can say it that way, as it is now. All right, so you can see the magnetic things in the picture there on the right. You see the moon uh, on one side of the Earth, and you see the moon on the other side of the Earth, and how that magnetic field works. All right, and there's an article there from uh, James Green in Science Advances about when the moon had a magnetosphere, or one that made a difference anyway. Okay, in fact, he said this, James Green, who wrote the article associated with that picture that you just saw. Green and his colleagues concluded their study by saying that for any planet to host life more complex than a few microbial species for more than a brief time, it must be part of an astronomical configuration virtually identical to the Earth-Moon system, with a virtually identical dynamical and magnetic history. It's important to add that such planet-moon system must orbit a star virtually identical to the Sun, given that the stars more massive or less massive than the Sun pose a significantly greater risk to any nearby planet's atmosphere and hydrosphere, and thus to life. So again, the moon and our moon is unique to this solar system and is unique in its capability of supporting life. All right, so have you been counting? How many royal flushes, if I can use that term, has our solar system, including the Earth, the Moon, and the other planets, received that allow for hosting and sustaining life on Earth? Not only for life in general, but for advanced life and for a technologically advanced civilization. How many times have we come up winners here? If you look at all these descriptions now of everything we've talked about so far, how many times does that come up? Where it's just like this one's just right, and that one's just right, and that one's just right. All right, using what we know of, of the surprise principle and the scale of probabilities involved for the complex requirements of advanced life, what sort of hypothesis would make sense of the increasing number of observations we make where the parameters seem to be finely calibrated for advanced life? All right. What are we to make of the apparently narrow time window during which the fine-tuned features that permit our existence and the existence of our global civilization opens and closes? What can we deduce from the fine-tuning about the attributes of the tuner? So clearly, I would say the deck was stacked here. This did not occur randomly because we see what random other things are in the other systems, and it's not even close. All right, I hope that was helpful for you. I know there was a lot of data. We kind of went through it pretty quickly. I want to give some additional sources for reading if you want to get more into any more of this kind of data about the planet or the universe and that sort of thing. These three books, all by Hugh Ross, The Creator and the Cosmos, Improbable Planet, and then the most recent one, Designed to the Core. I highly recommend these. All of them are dense, full of scientific data, and I mean, really hard science here. This is the scientific stuff. Hugh Ross is an astronomer, an astrophysicist, so it's full of scientific data. A couple other things I would reference. This book called The Blackwell's Companion to Science and Christianity. This has a lot of good bridge points, I guess you could say it that way. Uh, Stephen Meyer wrote a really interesting and thorough book, and I've read this one, but he published it in 2021 called Return of the God Hypothesis, Three Scientific Discoveries That Reveal the Mind Behind the Universe. If you want to get into some good science reading here, read this one. I have lots of other recommended reading. You can see some by Hugh Ross, some by some others. In fact, some of these others we might hear from them in the future. Some more recommended sources. These are almost all NASA. I think this whole page is almost all NASA. Um, there wasn't an account in 1859 of a solar flare and what effect it had. So that was interesting. So that's what I've got for today. And thanks for joining us. And if you want more topics, I do have other topics that I can talk about, and I've got a source for them there. So if you want to email me either about the uh, stuff we talked about at the beginning about the Nature article from the previous, the follow-up from the previous meeting, or anything else, there's my email address. And thanks for joining us today.